So we're looking at matrices, or the plural of matrix. See it somewhere. So before we can get into this, the idea is that we can a system of equations, or specifically a system of linear equations. I don't think you can do matrices with nonlinear stuff. Is that a lot of businesses would need to keep track of a lot of things in order to keep production, especially something where people make something like a manufacturing business. That if you decide to increase the amount of product A that you're making, that's going to cause you to use up certain materials more, or and since we don't have an infinite number of machines, we don't have an infinite number of people, we don't have an infinite number of time. If you start increasing one area of your production, it's going to end up taking away from another area of production. If you make multiple things, and so just kind of the idea that changing one thing in your system could have ripple effects through other things, and so just that you might have multiple variables within your business that you got to keep track of it. And so in order for a business to do that, they would end up using a matrix. And now, of course, they would end up typing stuff into a computer, and the computer would do all the matrix stuff for you. But that's what it's all based around. It's the idea of a matrices and a bunch of really large systems of equations, essentially. But we saw how time intensive and tricky it was just to solve a 3-variable system of equations by hand. Imagine solving a system of 5 equations with 5 variables by hand. It would just be really a lot of work. And then you could go up to 20 equations with 20 variables. It's just, you get really big things. And matrices can make all of that much simpler. Still solving a 20 by 20 matrix would be difficult, but matrices plus computers makes much more easy. So, but looking at a 3 by 3 matrix, solving that can be quite a bit simpler than solving a 3 by 3 system, even though they are the same thing in the end. Just because the way we can manipulate matrices is a little bit quicker. So, okay. So first we want to talk about though is how we can manipulate a system in a slightly different way than what we were just doing with the elimination and the substitution. Okay. So here we have a system of equations just like we would have seen on Monday, Tuesday, and here we have what's actually the same system of equations but written in triangular form. Okay? And it's called triangular form because this little missing triangle here. Okay, that's why it's called triangular form. But what we see here is that the second equation does not have an x value, and then the third equation does not have an x or a y value. And they asked us this rather rhetorical question, which one would we rather solve? When it's obvious we'd rather solve this one. So how would we solve this equation or system of equations? You guys think, how do we solve this? What do you mean, Rhea? Substitute what? Okay, so plug z into the second equation. And what's gonna be the goal there, or the point of doing that? Okay, so plug z into the second. To find y. Okay, so we plug z into the second equation to find y. Then what? Okay, so then we're going to say plug y and z, plug into the first equation to find x. Okay, so there's our plan. Right? That's what we want to do, so let's go do that. Let's plug z into that equation. So y plus 4 times 1 plus 5. So obviously y equals 1. We already knew that z equaled 1. Let's go just write that down there. And then plug y and z into the first equation and solve for x. So 2x plus 1 minus 2 times 1 equals -7. So get down to 2x minus 1 equals -7. So if I add 1 to both sides, get 2x equals -6, and then divide by 2, x equals -3. So we have our three values there, and just like Monday, Tuesday, we need to write that as an ordered triple. So x, y, z, so -3, 1, 1 should be our point where all those lines cross. So we can check to see that it actually is a solution to this system, and they actually have the same solution. So plugging in -3 for x, that'll give us -6, and then +1, -6 plus 1 is -5, and then that'd be -2. So -5 minus 2 would be -7, so it works there. -3 plus 1 would be -2, plus another one would be -1, so -1, check. And then -2 times 1 would be -2, -2 minus 1 is -3, -3, check. Right, so that's the solution for this system also. Okay, so we see here that these are called equivalent systems. Okay. So here they're talking about operations. We can use certain operations on a linear system to create an equivalent system. So that's essentially what they're getting at, is that this system here was manipulated, operated on to get this system, and then they are equivalent systems because they have the same solution. So equivalent systems are systems with the same solution. As the original. Right? So an equivalent system has the same solution as the original system. So how can we manipulate a system of equations without changing its answer, right? So to get an equivalent system. So the first thing they're saying that we can do is just interchange any two of the equations, right? So if I wanted to, I could just take the system and say, well, that's the first equation, that's the second equation, but I just want this one to be the first equation and that one to be the second equation. We can just take them and flip them if we want to. Okay? Hopefully that makes sense, that the order that the equations are written in doesn't matter. Us moving them around doesn't change anything. Okay? I can take that whole equation and flip it down there, and I can take that whole equation and I can flip it up there. No big deal. We can multiply any of the equations by a non-zero value. We should understand that because we've been doing that. Right? Every time we solved with elimination method, we were saying, well, let's multiply that first equation by 2, and then, right, it's okay to do that. Right? It just can't be 0, because if you multiply by 0, that just kills the whole equation, and that's not okay. But we can change the equation as long as we multiply, in a balanced way. And then we can add one equation to another equation, which again we should be okay with because we've been doing that. Right? Let's multiply equation 1 by 2, and then add it to equation 1, and it'll kill the x's. Right? We've been doing these two. So number 2 and number 3 should be very familiar to us. And hopefully number 1, you're like, okay, yeah, the order doesn't matter. We can do that if we want to. Okay? So those are the things that are okay to do to a system, and they won't change the answers. Okay? So what we're going to talk about here on the next page is how do we use those operations to take a system and rewrite it into triangle form. Okay? So we're going to manipulate this system to get it into triangle form. Okay? So we want, just like what's happened from here to here. Right? How did this get changed to become that? Okay? So we're talking about how that process happened. So the overall idea is that we don't want there to be a value here, here, or here. Right? Those spaces should be empty to be in triangle form. Right? There's no x value, there's no x value, there's no y value. We want those to be gone. Okay? That's the overall idea. And that's what this is talking about. So it says, eliminate the first variable from every equation except the first. So how do we get those x values to go away? Okay? So I want those to go away first, right? So we're going to use operations to make that happen. And then we're going to shift attention to the second variable, and we're going to eliminate it from all subsequent equations. So they're using language here that would tell us that if we had a system of 5 equations with 5 variables, we could do this process with a very large system. We aren't going to do that. We're going to max out at 3 variables, three equations. Okay, but so we could keep doing all of this over and over again to eliminate variables, eliminate variables, eliminate variables if we had a whole bunch of variables. Okay? But what we need to do is find a way to get rid of the first variable, which to us is just always going to be x. And it doesn't matter if that's x and y and z, or if that's a, b, and c. It doesn't matter. But we generally use x. So how do we get rid of x twice? And how do we get rid of y, the second variable, once? Because we're only going to have one subsequent equation. Okay, so that's what it's talking about. Okay, and the other thing we want is for these, it doesn't really do a great job of stating it here, but we want these coefficients here to be 1. Okay, so we'll want that y to have a coefficient of 1. We'll also want the z to have a coefficient of 1. It's nice if the x here also has a coefficient of 1, but it's not necessary. But you do want this to have a 1, you do want this to have 1, and it's just kind of a bonus if you can get that to be a 1. But again, not necessary. All right, so I also need to introduce you with a little bit different notation. So when we did this on Monday, I said, hey, the first thing we want to do is just label things so that we can talk about them easier. Say, hey, this is equation 1, this is equation 2, equation 3, right? And so I was just doing this, saying, right? With these, it's a little bit different. Okay, and this is what we'll do with, this is the same way we're going to do this with matrices. So we're just starting to learn some of the notation for matrices. So with matrices, we don't say equation 1 and equation 2 and equation 3. It's row 1 and row 2 and row 3. So this would just be R1, R2, and R3. Okay. So they refer to them as rows, not equations, because once we get to a matrix, they won't have equal signs in them anymore. They'll look a little different. So they'll just refer to them as rows. Okay. So now we just have a quicker way of referring to them. But we need to find a way to get rid of one of these x's. And it's essentially like when I had you guys going back to Monday, I said, hey, we need to find a way to get from 3 equations, 3 variables, to 2 equations, 2 variables. Right? We need to eliminate something twice. Right? So now we'll just have y's and z's instead of x's and y's and z's. This is just a little bit more prescribed. It's saying get rid of x. Whereas we were saying, well, which variable do we want to get rid of? Now we're saying get rid of x. Okay? So it's just a little bit more prescribed. So how can we get rid of x? Well, what are we allowed to do? We're allowed to interchange things. We're allowed to multiply rows by numbers. We're allowed to add rows together. Well, we add these rows together, won't the x's go away? Okay? Now we can't eliminate both x's at the same time. We can only do one thing at a time. Or we can do more than one thing at a time. We shouldn't do more than one thing at a time because we're just learning how to do this. Okay? So we're just gonna do one thing at a time. If you get really good at this, you can do multiple operations at a time. Okay? Not where we are right now. So in line with row 2, I'm going to write row 2 plus row 3. It's going to be, so leads to, whatever, how you want to say that, just an arrow, okay? Leads to row 2. So basically what I'm saying here is to get a new row 2, I'm going to add row 2 to row 3. Okay? So I'm creating a new row 2. Okay? That's going to be without an x because those will cancel. After I decide what I want to do, and it's really important for you guys to rewrite the problem as far as the parts you're not going to mess with. Okay? We're messing with row 2, so I want to rewrite row 1 and row 3, and I can go and focus on row 2 later. Okay? But I don't want to accidentally mess up row 1 and row 3 with my thinking. We're just doing one thing at a time. So, always with stuff like this, transfer errors can be huge. So you just want to be really careful about making sure you're writing the equations back with fidelity. Okay? So those need to have transferred over exactly as they were. Then we'll say, okay, now I want to go and do this math. Okay. And I'd really suggest you guys would be using your fingers as you're doing this. It's hard for you guys to see me doing that since I'm doing it on the iPad. But I'm putting my one finger here and I'm putting another finger here just to make sure I'm keeping my eyes in the right spot, because there is a lot of stuff going on. I don't want to accidentally look up here. Okay, so use your fingers to help guide you, but I need to be looking at that first. Right, x minus x. Of course, that goes away. So then I slide it over to the right a little bit. Now I'm looking at negative y plus 2y, right? Because I'm just adding them together. Negative y plus 2y, of course, is 1y. That needs to go in the y column of my new system. So 1y. There. Don't shove it over here to the left. Keep it in line. Then I'm going to slide my fingers a little bit to the right, looking at the z's. Z plus z. So that's 2 z's. So positive 2 z's. And slide my fingers a little bit to the right. Now I'm looking at the equals 2 and equals negative 3, and those are getting added together. Right? Everything's addition. So that would give me negative 1. So I've gotten one step closer, right, or I've only done one step, right, to getting in this in triangle form, because now that x value is gone from there, which is what we want. We want this space to be empty. So now we need to find a way to make this x go away. I'm not allowed to backtrack and say, what if I did something back here with it? I'm not allowed to do that. I have to work where I am. Okay? So how can I manipulate the equations that I have to make this go away? Well, I have a 3x up here, and I have a negative 1x here. I could multiply this row by 3, then I'd have negative 3x's and positive 3x's, and those would cancel. So just like we would have with the systems of equations on Monday, right? And multiply this row by 3, and then I'll add it to that row, and I'll have a new row 3. So how do I note that? How do I say that? I'm going to do 3 times row 3 plus row 1. That's going to be my new row 3. 3 times row 3 plus row 1 will be my new row 3. Once I have my plan made, I need to rewrite the stuff I'm not messing with. So I'm not messing with row 1. I'm not messing with row 2. I'm going to bring that down into the left a little bit just because I don't have much space there. So if you guys have more space over here, you can write it over there. I wrote kind of big this time. So again, as I move all this stuff, I need to make sure I don't do a transfer error. So 3x plus y minus 2z equals 2. Then my second row, y plus 2z equals negative 1. Okay, so there's the 2 rows I wasn't messing with. And now I can go back and worry about that third row that I am messing with. So here's where you guys need to make a little decision for yourself. Like, where are you going to do this work? Right? Because we need to multiply row 3 by 3 and then add it to row 1. In the past, we would, rewrite the whole thing. I multiply this by 3 and then bring it over here and then bring this one over here. But you're really not going to want to rewrite and rewrite and rewrite. It's going to drain you. Okay? So where are you going to do it in this space that you have so you don't have to rewrite the one that we don't want to change? For me, I like to do it just right below or right above. Like this is the one I want to add it to, so I might put it right above here. Okay? Or this is the one I'm multiplying by 3, so I might just do it right below it. Okay? So I'm going to multiply the bottom one by 3. I'm just going to do it right below where it was. So again, I'm using my finger to make sure that this number times 3, this number times 3, this number times 3, this number times 3. I don't want to accidentally grab something else. Use my finger to help keep my eyes focused. So negative 3x plus 6y plus 3z equals negative 9. So There's that equation multiplied by 3. Right there. Now, because I chose to put it below, it's this equation here that I'm trying to add to this equation. There's a lot of stuff between them. You definitely get confused, okay? So with your brain, because of where I chose to put it, I need to, my brain cancel these, cross these out. I don't want to cross them out because if I did make a mistake and I had to go back and try to uncross stuff out, it's not going to be good. Your eraser's not going to work that well, okay? So you don't want to actually cross them out, but you just need to really make sure that, or use your fingers, I'm putting my finger here on this, and I put my finger here on this, make sure my eyes are staying focused in the right spots. I don't want to grab that 2y and try to add it here. It's this 6y that I need, okay? So either you're touching your paper to keep your eyes focused or something like that, but you don't actually want to cross them out because that could lead to bad things if you made a mistake. So, okay, so, and then that answer needs to come down here. So 3x, negative 3x, those cancel, so nothing there. Y plus 6y, 7y's. Negative 2z's plus 3z's, that's 1z. And then 2, negative 9, give me negative 7. So now we've gotten rid of this x, we've gotten rid of that x, right? So what we wanted, we want no x values there. I guess we're getting closer to that triangle form. So what we need to find a way is to get rid of that third y. That needs to go away. So how can I use what I have to manipulate this y to go away? Okay. Well, I can't use the first equation because the first equation has an x in it. If I try at all to try to add this equation to this equation, it's going to give me an x back in, and I don't want to put an x back into it. The only thing I can use is these two because they're the only ones that don't have x's now. So how can I manipulate these two equations to make this y go away? Throw that out to you guys. How can I manipulate these two equations to make that y go away? Okay, multiply the second equation by negative 7, then what, Victoria? We multiply the second equation, row 2, by negative 7, then what? Remember the three things we can do, right? We can interchange equations, we can multiply by a non-zero number, or we can add equations. You don't want to add to the first one because the first one has an x in it. So if we add it up here, that's not going to make that y go away. We don't want to add it to the third one. There you go. We're going to take negative 7 times r2 plus r3, right? If that was negative 7, that was a positive 7, and those would cancel. So plus r3. And that'll be our new r3, our new row 3. And that row won't have a y in it. So as soon as you decide what you're going to do, rewrite everything you're not messing with. So I'm not changing row 1, so I'm going to rewrite it. So 3x plus y minus 2z equals 2. Not changing row 2, so that was y plus 2z equals negative 1. And now I need to go back and do that math. So again, we said we want to multiply this equation here by negative 7. So where am I going to put that? I need to do that, but I don't want to rewrite everything. So for me, I'm just going to put it down here. I'll multiply that second equation by negative 7. I'm going to put it right here. That way I can add easily. So again, I'm going to make sure I focus on this y, this z, that number there. So use my fingers to help me do that. Keep my eyes in the right place. So negative 7 times y is negative 7y. Negative 7 times 2z is negative 14z. And negative 7 times negative 1 is positive 7. So I did this part of it. Now I need to add the two rows together. And that's going to go over here to the right. So I'm going to add those together. They cancel. Add these. Oops. These together, get negative 13z equals, and add these together, get 0. Okay, so here's our triangle. Right, so it's almost in triangle form. There's just one little thing that's not right about it. But we've gotten rid of both x's, we've gotten rid of the y. So what's not yet good is that this coefficient here on the z is not 1. That's a really easy fix. Okay. So we need to make that negative 13 go away. So the only things we can do are we can switch equations around, we can multiply them by some non-zero number, or we can add them up, okay? And me adding this to anything else is not going to be good because if I add it to the second equation, there's going to be a y again. If I add to the first equation, there's going to be an x and a y again. So I don't want to add it to anything else, okay? I just need to turn this into a 1. Well, how do I get rid of that? It's divided by itself, right? So I'm going to take row 3 and divide it by negative 13. That'll give me a new row 3. Without that negative 13 there. And of course, it said we can multiply by any non-zero number. Multiplication and division are really the same operation, right? I could say that I'm going to multiply by negative 1/13. And that's the same thing as dividing by negative 13, but I think this is easier for us to think about. We can multiply or divide by any non-zero number. This is about the only time I would ever tell you guys to divide is if you're just trying to get rid of a coefficient. And after you decide what you're going to do, I really, again, suggest that you immediately write down the stuff that you're not messing with. So we're not messing with the first row, not messing with the second row. So I'm going to write those down as they were. And then, of course, negative 13 divided by negative 13 is 1z. And 0 divided by 13, negative 13 is still 0. So there's our system in triangle form, or triangular form. But once we start seeing and manipulating matrices, we're going to be using these same thoughts. So all this thinking that we're doing here and all this writing as far as the notation is going to be the same notation that we use with the matrices. So it's very similar thinking to what we were just doing on Monday, and last week, right? All this elimination stuff, right? Just kind of focusing yourself on these variables. So once we have that done, now we can actually solve that system really easily. I just want to make sure, is there anything in these 4 steps that we did that you guys want to question, like why I did what I did or how I did what I did there? I'm guessing it's the first time you guys, or most of you, have seen all this, so it'd be kind of weird. Okay. So if we plug z back into the second equation, we have y plus 2 times 0, right, which would just be 0. So y must be negative 1. And then plugging y and z back into the first equation, so 3x plus negative 1 minus 2 times 0. So 3x minus 1 equals 2. So 3x must be 3. there's our order triple. I really should check that before I circle it, but 3 times 1 is 3, minus 1 would be 2. 2 minus 0 would still be 2, so 2, check. 1 minus negative 1, so it'd be 1 plus 1, so 2 plus 0 is 2, check. Negative 1 plus 2 times negative 1, which would be negative 2, so negative 1 plus negative 2 is negative 3, plus 0 is still negative 3, check. So solution to this system was the same as the solution to this system. So how did we, there's us manipulating this one to make it look like that. You good, Ruth? You Matt? You right there? Okay, so let's look at matrices here. That's not good. Okay. So we can use a matrix to represent a linear system of equations. Okay. Really what this is a lot like, guys, is when we went from talking about long division of polynomials to then talking about synthetic division of polynomials. Like, those processes look so different, but we saw how quick synthetic division was compared to long division. And part of that was because all we have to worry about is the coefficients, right? We set up our little box, and we just pull those coefficients out, right? And so that made the process a lot faster. And so we're going to see that same thing here. Like, once we get into it, that just having the coefficients and not all the variables is going to make things faster. Yeah, but we got to talk about some kind of vocabulary here, some rules about matrices first. So matrices are always set up as a rectangular array. Okay, each entry, so each of these numbers is called an entry or an element. So each entry or each element is referred to as this, like some basically spot. So the letter A doesn't really matter here, just could be any letter, but it's the I and the J that do matter. So basically what it would look like is you would say like A23, okay? And so that's not A23, it's A23, and the 2 represents something and the 3 represents something, so you can't just mush them together, okay? And so the 2 represents the I value, or the I part of it, which is the row that the element or the entry is in. So the I represents the row, and then the J represents the column. So when I say A23, I'm saying the element that's in row 2, column 3. Okay, so I don't have to say row 2 and column 3. I can say just A23, like, so we know to go to row 2, column 3. Okay. Because when we talk about matrices, we always talk about them in their rows first. So we say a matrix is represented by its, indicated by its rows. Come on. Okay. And then by its columns. So that's one of like kind of the conventions, right? Long time ago, whoever decided to do matrices first, said, hey, I'm always going to say rows first and then columns second. And that's just the way we all need to do it, so it's all the same. Okay. So when I look at this matrix here, it has 2 rows, and of course rows are sideways and columns are vertical, just like in a building. That's how I always remember columns go up and down. All right, and so then rows must go sideways. So the rows, there are 2 rows, and then 2 by, and then there are 3 columns. So this is a 2 by 3 matrix. So it's not 2 times 3, it's 2 by 3. That's how you say it. That's a 2 by 3 matrix. The next one here has 1 row and 1, 2, 3, 4 columns. So it's a 1 by 4 matrix. So when we get to later talking about how to add matrices together, how to multiply matrices, subtract them, stuff like that, you have to know how big they are. You have to be able to identify that easily. So just it is kind of important to know, just be able to very quickly say how big the matrix is, because only certain matrices can be added or subtracted to each other. Only certain matrices can be multiplied, and it all depends on how big they are. So you got to know how to say how big it is. So it says here in the first matrix, A12, the entry is, right? So where's this? Where's A12? So again, what that means is, what's the element that's in row 1, column 2? So row 1, column 2 would be 3. So A12 would be 3. That's first row, second column. It's like playing Battleship, essentially. So where would A21 be? What's A21 equal to? In this matrix only. 2. We'll be saying 2. So second row, first column, 2. What's A13? 3. Matt, what's A13? 0. First row, third column. Yep. Ruth, what about A22? 4. Yep. Second row, second column, 4. So that's how you want to talk about a specific element, a specific entry. That's how you would refer to it. What's the element in 22, or what's A22? Again, there's nothing special about the letter A there, just what they picked. Any questions about how to say how big a matrix is, or how to identify an element? So the next thing we're going to talk about is how to take a system of equations and rewrite it into what's called an augmented matrix. And all the augmented means refers to is this here. The augmented matrix has this line here, and the line just represents the equal sign. Like, we're just separating the constants away from the coefficients of the variables. So when we say an augmented matrix, it just has a vertical line through it there, and that just represents the equal signs. Okay. But the idea is that we're just going to grab the coefficients and the constant out of this each row. So as I look at that first equation, it's going to become the first row of my matrix. So since that's 1x, my first element is 1. That's 1y. That's my second element is 1. That's negative 1z, so it's the negative 1. And then I have my line. And then the constant over there on the far right is 1. So that's the first row of my matrix. As I look at the second equation, you should notice there's no y value. So there's 1x though, and there are 0 y's. So kind of like again with synthetic division, like we kept telling you guys, like make sure you identify gaps. You have to fill those gaps in with zeros. That second column of this matrix has to represent the y's. It can't represent the y's sometimes and the x's sometimes and the z's sometimes. That just makes the whole thing not worthwhile. That second column can only represent y's. So there are no y's, so I have to put a 0 there. Okay? The 2 can't go there. All right? The third column is where my z values go, so that's where the 2 goes. And then the last column is where the constant goes, the negative 3. Those gaps can mess with you, right? You just got to make sure they get plopped in the right spot. All right, what about that last one? What should our row in our matrix be? How do I write that over here? Okay. Okay. So Claire said 0, 2, negative 1, 3. All right. So there's no x value, so there's 0 there. One thing we need to do to finish that up is just put it in brackets. Matrices are always in brackets. That's definitely the main skill you guys need to have, is how to go from system to a matrix. Because you'll be given a system, you'll need to rewrite, and then we'll manipulate the matrix, or you'll come up with your own system because it's a word problem, and you'll turn it into a matrix, and then we'll manipulate the matrix. So again, once we learn how, this manipulation here will be faster than how to be able to do it here. So you won't go this way as much, but let's go ahead and do it. Okay. So how do I take a row out of the matrix and rewrite it as an equation? And again, it doesn't matter actually which variables these are, but this, we could say it's A, we could say it's X, we could say it's B, we could say it's Y. It doesn't matter what letters we use. And it actually, mathematically doesn't matter which column is X and which column is Y and which column is Z. It's just that if everybody put X's in different places, then nothing's going to make sense. Okay, so we all just need to agree that alphabetically the first variable would always be the first column, the second variable alphabetically would always be the second column, just so that things don't get jumbled. Like the numbers don't care where they are, as long as these are all Z's or all C's or all P's, whatever letter you pick, as long as those are all B's or M's, it doesn't matter. As long as they're all the same variable, it doesn't matter. They don't care which column they're in. They just want to be with their family. Okay? But we don't want to get them all mixed up, because that would just be bad for us. Okay? So we just need to agree that we're always going to go alphabetically. So there's one X, so X. There's one Y, so plus Y. There's two Z's, positive two Z's. And then that's equal to, that's our line tells us where equals to 4. There's the first equation from that matrix. Katie, what about the second equation? Okay, so 3x plus z equals 2. We always want to write that in the simplest way possible, right? We know there are no y's, but we wouldn't write that there are no y's. Okay? Our equations should always be written in the simplest form, just like here, right? We didn't write that there was no y's here. We just didn't write y's. Okay? When we have a matrix, the gap is really important to fill. But over here, we know what to do with that. We don't need to worry about it. Okay, so yeah, good job, Katie. Wes, what about the last equation? All right, so Wes said 5x plus 2y minus z equals -2. All right. Anything there about going from system form to matrix form, or matrix form to system form? You guys worry about? You okay, Tiger? Maddie? Okay. All right, so this last thing here, yep. So row echelon form is really the same thing as triangle form. So if you notice this here, the other way. Here's that triangle, right? There's no x, and there's no y. So this row echelon form is the same thing as the triangle form. So we can manipulate a system into this, we're manipulating into triangle form, okay? The only thing that's different here is that these numbers do need to be 1. So I said on the triangle form that's nice if this number is 1, but it's not necessary. For row echelon, that number has to be 1, this number has to be 1, this number has to be 1. Okay, so when it's in row echelon form, those are always 1s. And then the 3 zeros in the bottom left corner. Okay? We'll talk about how to get it there tomorrow. But what we're going to do right now is just taking this and rewriting it back as a system, then solving that system really quickly. And seeing that once we can get into that form, it's very quick to solve. So there's 1x plus 4y's minus 2z's would equal 7. since we're short on time, I'm going to just finish this. So there I have 0 x's, so just 1 y plus 5 z's equals 0. And then that bottom row, 0 x's and 0 y's, and is 1 z equals -2. This is actually a really important row, because notice how it doesn't have any x's or any y's. That means there's 1 z, right? Z is -2. That's exactly what that says. Okay, so it's really important to have a row like that, or really helpful to have a row like that. If you guys had another matrix that just random number, random number, random number, random number, okay, but then it was 0, 1, 0, 5, and then number whatever. What this is telling you, just by looking at, I have 1y is 5. Y equals 5. All right, so having 2 zeros and then a 1 lets you know exactly the value of that variable. That's a really important row. We know exactly what it is. Okay. You really like to have those 2 zeros and a 1, and then whatever the number is on the other side is just the value of the variable. So, okay. So we can do just like we've done. We can plug a z in, find y. So y plus 5 times -2 is 0. Y minus 10 is 0, so y must be 10. And then I can plug in y and z to find x. So x plus 4 times 10, which would be 40, minus -2 times -2, which would be 4. So x plus 44 is 7. So x must be what, -36, 37? So there would be our solution. So tomorrow we'll start talking about how to do row operations on a matrix. It'll be very similar to what we did earlier with the row operations on a system, so that we can get a matrix